stoichiometry. That's our introduction. Okay, so we're going to learn about stoichiometry. I hope you're not super hungry, because food makes for a good analogy for stoichiometry. So we're going to talk about BLTs. So putting together a sandwich, if you're following a recipe, follows in a similar line of thinking as stoichiometry. All stoichiometry is looking at the numerical relationship between our chemicals. So how many of each chemical do we put in? How many of each chemical do we get out? So it's just talking about balanced chemical equations. We're just looking at what are the coefficients, what are the numbers in front. And it's a lot like making BLTs or other sandwiches. So part of the reason that we do this is so that we can look at, okay, how much of an ingredient do we put in? How much of the product can we get out? So like if I'm making sandwiches and I only have 3 pieces of bread, assuming I'm not making open-faced sandwiches, I can only make really 1 sandwich, or I can do something Big Mac style, right? I can have a Big Mac style sandwich with the bread in the middle. That's all we're doing. It's just how much can I make with how much I've got, or how much must I have had to start to make how much I had. It's not as complicated or scary as it maybe looks like it could be. And now we're going to hopefully appreciate these little cutouts that I made that took altogether way too much time. So like stoichiometry, a recipe, like for making BLTs, gives us a numerical relationship between the ingredients and the products. And I didn't just switch this. It used to be pancakes, but now it's BLTs. Okay, so when we're making a BLT, let's say that we really like our bacon. So we're putting 4 strips of bacon in. We got 1 piece of lettuce, 2 slices of tomato, 2 slices of bread, and that's, boom, 1 BLT. So we're just going to take this as our recipe for BLTs and then use it to talk about stoichiometry. So if we've got 4 slices of tomato and enough of everything else, we can make 2 BLTs. And the way that we can figure that out is looking at the relationship between slices of tomato and BLTs as a ratio. So typically what I'm going to do for stoichiometry problems, I'll look at, okay, what's one of the things that we care about? We'll underline that. So we care about slices of tomato. So slices of tomato we underline in our reaction or in our recipe. We also care about BLTs. So we're going to go and find BLTs. So the 2 things that we care about are slices of tomato and BLTs. I'm going to omit the slice part. So 2 tomato goes to 1 BLT. We can use that as a conversion factor. So assuming that we just have tons of bread lying around, we've got lettuce, we've got bacon, we've got bread, all that other good stuff. Starting with 4 slices of tomato. How many BLTs can we make? Well, our ratio is 2 slices of tomato in, 1 BLT out. So we put 2 slices of tomato on the bottom in our conversion factor. We put 1 BLT on the top in our conversion factor. The units of tomato cancel out. And we've got 4 divided by 2 BLTs, so 2 BLTs. Any questions about how I did any of that? This is all we're doing in stoichiometry. That's all it is. It's just a big, scary Greek origin word. That's all it is. It's just what's the relationship between the numbers. Okay, great. We've got an example with 8 slices of tomato. Let's make it 8 strips of bacon. Okay, we've got 8 pieces of bacon. Assuming that we've got enough of everything else, how many BLTs can we make? What are the 2 things that we care about in this problem? Bacon. We care about bacon, so we're going to underline bacon in our recipe. What's the other thing we care about? BLTs. We also care about BLTs. It's the other thing that was mentioned. So we're trying to figure out, given a certain number of pieces of bacon, how many BLTs can we have? So to solve it, the two things that we care about, the two things we underlined, we're going to pull those out and make that a conversion factor. So we take 4 strips of bacon. If we have 4 strips of bacon, we can make a BLT. So 4 strips of bacon effectively equals 1 BLT. That's our conversion factor. And we're starting with bacon, so our conversion factor is going to be 1 BLT over 4 strips bacon. That's the conversion factor that we're going to use. So starting with 8 strips of bacon, 8 strength bacon, use our conversion factor for bacon on the bottom, 1 BLT on the top. 8 divided by 4, the bacon cancels. We can make 2 BLTs. It will get more complicated, just a little bit. Do we have any questions before we make it a little more complicated? All right. The way that we can make it more complicated is by applying it to actual chemicals. So probably easy for you to imagine what strips of bacon look like, what a BLT looks like, maybe even how they taste, how they smell. Delicious, right? Not the same, I'm assuming, for H2N2 and ammonia, or a lot of other chemicals. And so it starts to become a little bit more abstract. So we need to trust the process. We're going to do the same steps. We just don't have a sense for what hydrogen and nitrogen and ammonia taste like, probably. So this is effectively, this is a recipe for how we can combine our hydrogen, our nitrogen, and make ammonia. Anytime that we're doing stoichiometry, we need a balanced chemical equation. It has to be balanced, otherwise we'll get the wrong answer some of the time. So we've got a balanced chemical reaction. Our key, or our clue, is that we've got coefficients. So generally speaking, if there are coefficients, if there's numbers in front of the chemicals, it's already balanced. If there are coefficients, safe to assume it's balanced. Okay, so we can make a couple of ratios of different things here, right? We can make a ratio of hydrogen to ammonia, NH3. If we put in 3H2, we get out 2NH3. So we could use that as a conversion factor. Given a certain amount of hydrogen, we can make a certain amount of ammonia, assuming everything goes perfectly. We could also do a ratio of nitrogen, N2, 1 N2 to ammonia. We'd make 2 NH3. So if we put in a certain amount of ammonia and we've got plenty of hydrogen, how much ammonia, how much product can we make? We can also get one between our H2 and our N2. So we might say, I've got a certain amount of hydrogen gas that's going to be produced, or that's going to be in a chamber or something. How much nitrogen gas do I have to combine with that to get them to completely react? So that third one would be 3H2 reacts with 1 N2. And then we could make conversion factors out of those, dividing both sides by one or the other, putting one on top, the other on the bottom. Those are all the ratios, all the stoichiometry applications that we can use for this. So let's look at that in action. Let's say that we've got, it's the same balanced chemical reaction. If we have 3 moles of N2, how much NH3 can we make? So the two things that we care about are, one, what? What's our first thing we care about? It's the first thing that's mentioned. We've got N2. We were given a number of N2. And we were asked to find what? NH3. So that's the other thing that we care about. So the two things we care about, the N2, the NH3. So we underline those, and we can pull those out to make our conversion factor. So 1 N2 in equals 2 NH3 out. And that's where we get our conversion factor. So we're starting with 3 moles of N2. And we're trying to get to an amount of NH3. So we want to divide both sides by the N2 to make our conversion factor. So that turns into 2 NH3 over 1 N2. So what this is saying is if we put in 1 nitrogen gas, we'll get out 2 ammonia gas. Our N2s cancel. The moles doesn't change, so we get out 6 moles NH3. Do we have questions or confusions about that? We can also ask a different problem. How many moles of N2 are needed to completely react with 7.13 moles of H2? So in this second one, what are the two chemicals that we care about? We have H2, because we are given 7.13 moles of H2. And what's the thing that we're finding? Yeah, we're finding moles of N2. So that's the other thing that we care about. So we're trying to go from moles H2 to moles N2. So we want to pull out, up here in blue, our H2 and our N2. And how are those two things related? 3H2 reacts with 1 N2. And since we have H2 and we're trying to go to N2, just like converting units, we want the N2 on top and the H2 on the bottom. Our H2s cancel, and we'll have 7.13 moles N2 divided by 3. So whatever that number is. .38 after rounding moles N2. All right, a different reaction. Water forms when hydrogen gas reacts explosively with oxygen gas according to the balanced equation. So this is already balanced. We've got oxygen reacting with hydrogen to form water. How many, that's our question word, how many moles of H2O result from the complete reaction of 24.6 moles of O2? So we're starting with the O2 partly because it has a number with it. So 24.6 moles O2, we're trying to find the moles of H2O. So the two things that we care about are the O2, because that's what we're starting with, and we also care about the H2O, because that's what we're trying to get to. So O2 turns into 2 H2O. And we can make a conversion factor with that. So we're starting with O2, we need to get rid of the O2. So that means the O2 in our conversion factor has to go on the bottom. And the 2 H2O goes on the top. So if we multiply by 2 H2O over O2, the O2s will cancel out. And we'll get 59.2, 49.2 moles H2O. Any questions before we add steps? Okay. We're going to add a couple of steps. So oftentimes when we're doing stoichiometry problems, we're starting with mass of a chemical, we're going to mass of a different chemical. All of our examples, we've started with moles of a chemical and gone to moles of a chemical. So that lets us just immediately do the stoichiometry step with our balanced chemical equation. We're adding some steps. So from the stuff that we've been doing, the stuff we've been doing is this middle bit, the red bits, moles A to moles B. We're going to add on, starting with mass of A instead of moles of A. We're going to go to mass of B from the moles of B. So this bottom bit is what, or this middle bit is what we were doing. And part of the reason that our problems typically take this form, starting with mass and going to mass, is because we can't directly measure moles. You can't just like throw a sample on a balance and it'll tell you this is 4 moles of iron metal. You have to get the mass of whatever your compound is and then convert that to moles. And then at the end, we would also be measuring our product in mass, usually grams. So we have to add these steps on to the front and the back. So lots of molar mass calculations coming our way. All right, let's say that we've got this reaction. We saw this one at the, in last chapter. So we've got octane reacting with O2 to form CO2 and H2O. Does anyone know what kind of reaction this is? Does anyone remember? Combustion. It's a combustion reaction because we're reacting with O2 and CO2 and H2O are our products. So this is a combustion reaction. Is this a balanced chemical equation? Or do we need to balance it ourselves? It's balanced. How do we know it's balanced? It's got coefficients. It's probably balanced. People aren't messing around just throwing random coefficients in front of problems. It could happen, but it doesn't happen in this class. So it's already balanced. We don't have to do that. That's great. What mass of carbon dioxide? So we're finding mass of carbon dioxide. is emitted by an automobile when number 5.0 times 10 to the 2 grams of pure octane is burned. So this is basically just 500 but with 2 sig figs. And our octane is C8H18. Carbon dioxide, it has that di prefix, meaning that it's molecular compound, 1 carbon, 2 oxygens. So we are going to be starting with grams C8H18. We're going to have to do at least one step, and eventually we'll get to grams CO2. Now the thing about these chemical equations is that we're talking about the number of individual pieces, like the number of individual molecules, or we're talking about moles of molecules. So like sort of in our BLT recipe, right? We were talking about number of pieces of bacon, number of slices of bread. We weren't talking about the mass of the bacon, the mass of the bread, the mass of the tomato, the mass of the BLTs. Similar sort of concept here. So we have to do a conversion to get from the mass to the number of pieces. And our number of pieces in this case is going to be moles. So we'll go from grams C8H18 to moles C8H18. And then from moles, we just changed from grams to moles, so it wouldn't make sense to change back. So C8H18 is the thing that we can change. So our octane was one of the things we care about. The other thing we care about is CO2. We're trying to get to CO2 so we can convert to moles CO2. And then last but not least, we can convert from moles of CO2 to grams of CO2. So grams to moles to grams, which is a pretty common problem type for this class. To accomplish each of these steps, each of these arrows, we're going to need some numbers, some conversion factors. For our first arrow, for going from grams to moles, what do we use for grams to moles? Some type of mass. Molar mass. So we need the molar mass. And at the end here, you may notice we're going from moles to grams. It's the same thing, opposite directions. So we're going to need molar mass there as well. So we have 2 molar masses to come up with, one for C8H18 and one for CO2. And then this middle step, the C8H18 to CO2 step, we need the ratio from our balanced chemical equation. So 2 octane turns into 16 CO2. Do you have any questions about like the basic solution map, the path that we're going to be taking? Cool. So our molar masses for octane, it's 114.232 grams per mole. For CO2, it's 44.009. I'm just doing them because I don't want to bother explaining, and I'm assuming that you know how to do them. If you don't know how to solve for a molar mass, that's okay. Come to Logan's SI session or ask me during lab or after lab or some other time. Or go back and watch the other videos where we talked about it. You will not always be given the molar mass. Sometimes you will. It just depends on how nice I was feeling in the moment when I wrote the test. Okay, so to start the problem off, we are starting with 5.0 times 10 to the 2 grams C8H18. We have grams. We want to get rid of grams to get moles. So we have to divide by our molar mass. Dividing by our molar mass puts the 114.232 grams on the bottom, and the moles flips up to the top. So our grams cancel. If we stopped here, our units would be moles C8H18, which is where we want to be based on our solution map. Now we have to convert our chemical using our ratio from our balanced chemical equation. Let's say that we don't know which one to put in where. So we write in 2C8H18 on the top and 16CO2 on the bottom, and we don't look at it and we just keep going. Then at the end, we have to use our molar mass of CO2. So we're going to do times 44.009 grams per mole. Put an equal sign. Our moles is going to cancel our moles from earlier, and we're hopefully going to end up with grams CO2. If we go back and look at this, this is not a correct solve. So we've got the grams canceling with the grams, we've got the moles canceling with the moles to get the grams back, but we did not cancel out, we did not properly apply our ratio. So we've got C8H18 on the top, and we have it on the top in our conversion factor. Lucky for us, we haven't plugged any numbers into our calculator yet, so we're not losing any work. We just have to swap the top and the bottom here. So these are multiplying instead of dividing and canceling out. No big deal, we'll just swap places. This is something that you can always do for free with very little brain power. So now that we've swapped it, our C8H18, we've got one on the top, one on the bottom, so those will cancel out as intended, as desired. And so the units that come through are CO2 and grams. So a bunch of stuff to plug in the calculator. 500 times 16 times 44.099009, and then divide by the things that are on the bottom. So divide by 114 and also divide by 2. And the number that the calculator gives us would round to 1.5 times 10 to the 3 grams of CO2. Okay, then we'll solve this. Next time, you're welcome to work on it a little bit. Now, what mass of octane would be needed to generate 42.3 grams of water?